Bismillahirrahmanirrahim. Hello everyone. This is a complete SAP 2000 tutorial course. In this tutorial, I want to model a multi-story steel structure and also do a seismic analysis. And then finally, I want to do the design of this structure. And in the last, I will create the detailing of this structure. So why I use SAP for steel structure? So I feel that the SAP software is quite uh, good and also reliable for the steel structural design and analysis. And there is a lot of efficient method, especially the auto design of section and also automatic wind and also seismic load application. So these things became the reason why I use SAP 2000. Let me show the the plan of the structure we intend to model and analyze and design. So this is the structure. This is a typical steel concentratedly brass. We have a core steel brass in the center of the structure, and the parameter in other part is still moment resisting structure. So still moment resistant structure means that we're not adding some release moments here. The connection is quite rigid and fixed. And in the center, we will have one core area, one here and one this side, one here. In the previous ETAPS tutorial, we added a shear wall. So now we want to create a very resisting core area here. And instead of shear wall, we want to use bracing system. So the remaining part is in moment resisting steel frame. The cross section, I want to use IP section, which is European code profile, and a deck for which has a 15 centimeter thickness. We will utilize this just because we're not going to design this. Just we want to apply the self load of that floor to the structure, and also that remaining superimposed dead load and this live load to this deck. The seismic parameters is the seismic parameter is in the short period 1.23 J, or ground G is the ground motion, and in the 1 second is 0.82. You have two ways to apply this ground motion. One is you can give the zip code based on the AC17, and the second is you can give these two parameters and the remaining parameters calculated automatically by program. So this is the when we design the structure for the seismic, you should clarify what kind of system is. So I used a bracing system. In the code, we have some data. You can see this is a special concentrated bracing frame. We have a R factor. Let me tell you what's the R factor. It's called response modification factor, and as omega over strain factor, and also we have CD, deflection or amplification factor. And this is the seismic design category. So B, C, D is ordinary seismic design category structure, and the other is quite special structure. But when you utilizing this system, there is no limit to applying in the all 5 categories. So you have a wide range of using this one. So I use this one and I get these parameters for my analysis. So 7, 2.1 and 5.5. So I written here, and later we will apply this when we defining the earthquake loads. So the wind load is neglected in this analysis. In case if you intend, then just you can consider the Therian location and also the type of structure and the speed of the wind in that location. Now we want to model this in using SAP software. So this is totally 30 meters, HB as 6 meters, and we will first model this one and then draw these brasses, and then we duplicate these to other area. Now in the X we have 5 bays, in the Y we have 3 bays. So I can go to the here in SAP2000. You can use any version, the procedure is same. Now I want to create a new model, and I can ask a new model. In the new model, first of all, let's define the unit. So we use kilonewton meter, and the default material I used United States material library. I can ask just a blank, and now I want to use Cartesian grid. So the number of grid lines in X is totally, let me check one more time, so 1 2 3 4 5 6, so totally 6 grids and 6 grids, and in the Y is 4 grids because it's 3 base. In the Z, which is equal to the story of the structure, we need 6 stories, so totally we have 7 grid in the Y direction, in the Z direction. 7. Now here is the spacing. So the X is 6 meters, in the Y is 5 meters, in the Z is 3.2 meters. So the first grid line location should be 0 0, and we created the grid line. Next I want to now we can see we have 6 stories. In case if you can go to the XY, which is the elevation, in the XZ or YZ, this 2 is elevation, 1 stories, 2 3 4 5 6 stories. Now here we want to define the materials. We use steel A36, and I'm going to add new material using United States region. The standard is ASTM, and I use the first AST A36 or grid 36. So this is the first ordinary steel. In case if you have your own project, you can change it. Okay, now the next is I want to define the section. I want to use Euro section, so I can go to steel here, but here I want to call import new one. I'm going to import, and install directory you can select Euro, and this is IP section, and you can see all the Euro section is added, and you can select the material as A13. So I want to create input this all IP section, and this is IP section from 100 to there is two kind of, one is like 116, and this one R. So that means hot roulette still we're not using this one, I'm using the ordinary profile, and I can go to select to this number, and okay. So I added this IP, and now I'm going to add new property, and I'm going to click auto section. It's called auto IP sections. So now I can select the all, but except that roulette part. So not some is roulette, some is V. So I'm going to turn off them. So that's ordinary, and that or is some abbreviation and meaning, I'm not sure, but this is ordinary IP. I'm going to add them. So this is my section which I defined here, and that's it. Okay, and I'm going to okay this one, and the next is I want to define another section, the same properties, but this time I want to select add new property, and I'm going to back to here for brassing. So we use the same let's use the same which we already defined for brassing and secondary beams and entire structure. Now we're going to go to define one more section for deck, and it is called area section, and we have shell, and I'm going to call add new section. So you can use this one in case if you're not using a deck, the system is a little complicated, so I can use a concrete slab. It's called Slab, but both we're not designed in this program. So we're using the concrete, this one, and the thickness is 50 centimeters in bending and also in. Now we define this one, and next we want to model this one. So here is you can see here is the last floor, so I'm going back to first floor, and now we are in the first floor, and we're gonna select it here. This command is called quick draw beams, and when you select here, and you can select, and then this windows appear, and you can select the predefined section. So we define auto IP sections. So for the entire structure we do this one. So the first one is let me select all, and now you can see the entire first floor beam is added. And the second one is I want to add some, it's called quick draw secondary beam. We use the same section, and we selected pin, so that means automatically the program will define release moments instead of define moment. So that one was fixed or continuous. So I'm going to select this one. You can see it's called number of beams, it be 3. We're not expecting 3, we're going to use 2. So when I comes to this floor, you can see here exactly the same. So we do to this one, but except this one. Now we finished the beam, secondary beam, and also primary beam. The next thing is that let's go to draw the columns. So we can go to the one of the elevation. So let me go to the elevation 1. I can go to the here YZ or XZ and YZ. If I XZ is this one and YZ is this one, so I'm gonna XZ, and here I can select all this. Sorry, it's not primary. We should go back to this one, the first one, again, an IP section. The modeling is a little complicated than the etaps. Now here is in the XY, in the Y15, which is if I go to the plan, the one should be in the plan. Let me this one go to the XY, and I should go to down. Now we can see where we are. If I select this one, so here is no appeared. Now I can go back to this one using this command here, and the second columns. So the better thing is you can duplicate as well, or I can manually draw. One direction, one side is in a longitudinal or X direction is finished. Now we want to model in the Y direction, so I can go back to this one. It's called YZ here, and select YZ, and this is YZ. Let me go to one in a 3D to see exactly. So actually all of them is finished. So the next I want to draw the brassing. So now we're in the one we need to in this base, and one here and one here. So I can go to first YZ and selecting, it's called brassing. This one is brassing, and I should select inverted V or V, and the moment release should be exist, so that's going to be pin. And let me bring this one in a 3D because we should observe that drawing here. Back to here, we already selected the section as IP section, and here when I select when I come to this area, this here, then here is the selection should highlight. So let me draw one here. So now we have the location. Now we can, in a 3D, we can observe we are in that grid, which is not correct. So I'm going to here one more, going to be a little further. So now we are here, and I'm going to give one more here, and here is the lighting, and we go one more, and here is also we need to define a brasses. So this side is finished. We go to back to this. So I'm going to turn off, and I'm going to back to, now we are in here lighting, and the last one is I have to delete this one. One further. So I need to delete this one, and this one is deleted. So now we need one brasses here. I can go to the XZ, which is another one, and now we are in this one. I'm going to be move one. Now it's lighting in exactly in this grid. So we need to define one more brasses here. So now we are okay. So the last thing is I go back to the floor area, the first floor, to define the opening and also defining the slab. I go to X Y, so this XY, and we are located in the right place. And next I want to create the rectangular area, or using this quick draw area. So I'm using rectangular area and using that slab and selecting this point, so I have created this one, and now I want to do one more things. I have to select this one, and here instead of slab I should select none. Select this one and this one here. Okay, and now I can check here. That's not okay, and I should go back to here again, and this time using none. In previous etaps there was opening, but now it is using none. So that means we don't have any slab area, slabs in this region. So now you can see it's two shell. One is that one, and the second one is shell 2, which is none. If I go to the shell 2, or maybe it's coincidence together, so I can delete them. And again I can draw using draw polyline, and this time I use first slab, and using this point, this point, this point, this point, this point, again this point, this point, and again this point. So again this point here, and the last point. And now I can so we couldn't create the slab. Let me use this method and this one, using slab, and yeah, this is better. So each primary beam will create one slab, but except that core area. Now the slab is created except the core area. So now we are done here. So the next thing is that I want to select these beams and columns, and as well as the brasses, then duplicate to here, to middle of this point. So I can go to again to the YZ, and YZ, and I can go little front, I locate it here, and so now I'm located in this area, and I can select this one, and including the beam. So now what I want to do is I want to replicate this. This direction is x, so the total length is 6 meters, so I want to give 3 meters. I'm gonna OK. So I created this brass with beams and also column. Now we are done in the first stories modeling, and I want to do one more thing. Then I'm going to select define the load in the first floor instead of the entire structure. In the load pattern, I should define 3 kind of load. The second is called super dead load or superimposed dead load, and you can call it we have dead load, and we should call it more. And when you select more, you can see super dead load. So I'm going to call add, and here is the live load. Live load, I can select live load, and the second is EX, which is earthquake in the X direction. It's called quake. The code is I use this code AAC7, and next is Y. Now we want to define the load, lateral load. So this is using global X. This X, we're considering some eccentricity, and also the first one is for the steel. You can use this one, and here the short period is giving 1 point. Let me check the data here. 1.23. 1.23, and this is 8.2. The site class is as stiff soil, and the other parameters as well-determined program based on this data. So this is 7, and this is omega is 2.5, and this is 5.5, and this is the office or residential office building is 1. Okay, and the same for the y direction, called modify lateral load pattern, this time using x 1.23, and this is 2, and using stiff soil, and this is 7, and this is 2.5, 5.5, and 1, 5.5. Now we define the entire loss. I'm going to OK. Next, I'm going to select it. Here I can go to the properties, then go to the area section. I want to select the slab. Select slab. Now the slab is selected. Here you can see I want to assign the load. Assign. Here assign shell or area load, uniform shell, and the dead load is self load of the structure, and I'm adding some superimposed dead load, and it is 0.8 kilonewton per 0.8 kilonewton per square meters using a gravity, so do need direction apply. And the second is going to previous selection and using live load, and this is 2.1 kilonewton. 2.1 kilonewton. Okay. So this is finished, and we can check to see if the load is added or not. Right click in the load, you can see 0.8 and 2.1. Now we finished the modeling and also applied the load. So the next is we want to select all. Select all, we go to the replicate here. Now we want to replicate in the z direction, which is the height of the structure, 3.2. So the number is upper story 5 stories. I'm going to apply it, and the entire structure is created. So the last thing, we go to the upper stories in the last floor. We go to the xy, to the xy plan, and that should be last floor. We want to add one more slab. This is 0, and this is 9.2. So what we're going to do is I'm going to back to here. It's called quick draw area, and I'm going to draw one area slab section, and I added one. So here I want to select this slab in the first floor. I selected them, all these slabs. So it means here is no slab. So I should draw one more slab. Okay, now I should go to take this slab and select it and replicate to the bottom. Going to be minus 3.2, and using 7, should that go to the down floor. So if I go to 1 story bottom, and I can see here is slab. Now I can go to select all slabs because there was some mistake in the one slab was missing, so we need to assign the load again. Assign and frame area load and uniform shell, and we're using this live load. I'm going to apply and previous selection, and this time using superimpose date load, so 0.8. okay, and we go to back to the upper stories. We can normally manually select this slab, and now I want to reduce the live load here. So this is the live load, and I'm going to assign again to the area and in frame shell load, and here instead of 2.1 I'm going to give 1 as a live load. It will replace. Okay, now it's completed, so we go to back to the first floor to define some but before this, let me define some other things such as the diaphragm. So I can select select properties all area, and I'm going to assign. Here is called area, and I can go to add diaphragm, but the diaphragm we should apply from the joint here. It's called constraint. In the previous one, we should define a constraint joint here. That is go to using diaphragm now in the Z direction, so that be okay. And we cannot apply now because it's here. We should select each node of that floor. Mostly for this kind of structure, because the concrete slab is not suitable for this structure, just we want to utilize the load of this structure, so we don't need to define diaphragms because that still is creating a frame, so we don't need a diaphragm in that one. But in a steel structure, so we need to joint or consider a very rigid area, horizontal area with the vertical and other direction. So we can ignore, or even we can select all in case if we want. Then we select all, and I'm going to back to assign in joint. I'm going to constraint here, and in a constraint we're adding diaphragm in Z direction. So we define this one diaphragms in the Z direction. Now the next thing is that we should go to the first floor and define the boundary condition or fixed base. Now this program can utilize foundation. Now we, instead of the fixed base, we can use the foundation, but we will ignore it in this tutorial. Next tutorial we will consider to add foundation instead of the fixed base. So now assign, I'm going to join, it's called restraint. So now I use this one, is it fixed? But most we usually use a joint connection or fixed, so fixed is okay. Now the modeling is completed. So for the to verify our work is okay, we want to define a model case to see how the time period is working. So in the load case, in the model, I want to create some parameters. Let's using raise factor. We want to consider acceleration in UX having 99% the mass participation in the Y as well as 99%. So we need to utilize the mass. So this mass comes from the self weight of the structure, but we want to consider the dead load, live load, including self load. That 12 is enough for this structure. And we're going to back to here in the mass source. We change the mass source to using a specific load. The dead load is 100% and the live load is 25%. Okay, and this is okay. Now we're finished. We can save the model. We can save here and code tutorial SAP2000. And now we can run the analysis. And here ask me to run. We want to run all the load cases. Now the analysis is completed, and we can display some output. You can go to the display here and show table. Call the analysis output, and we can see the model analysis to see how the result is work. Go to model here, and from the we can select mode. First mode. Let's see. So this is it. The time period 0.1x. So it's almost acceptable for the steel structure, and we can create 3D, and we want to turn off this one. I'm going to go to second mode. I think that diaphragm is causing some problem. So from this time period, I am not satisfied with the result. So I want to change that. I'm going back to here, unlock the model, and I want to select all again. Select all again, and I want to go to assign, and it's called join, it's constraint, and I'm going to give none. Now just by this changing, and I'm going to run the analysis again. Because the result that should be now, it's I feel better. So it's about so in we have one equation that's called 0.1 times n, so that's the number of stories times 0.1. So they say it equal should be 0.6, so it shouldn't be less than, but it's very close, 0.7, which is acceptable for me. And now this is okay. So the next thing is let's see some other internal force in the beam column from the earthquake impact. So this is the earthquake impact in the X. I'm using moment 3, and this is the moment in the beam column, and we want to see the axial force in the brasses, and you can go to the here using axial force and apply. So this is the axial force mostly in that brasses. So now we can even select this one, so it should be very small, so it's column, you can see very less, but the axial force in the column is quite large. If I go to select this one, and here is about 75 megapascal. Now I want to go to the design part, but let me define some combination. So this is the combination, and we're going to add default design combination. What we're going to do is we want to design steel frame design, so we cannot do anything else here. So this is created, you can see 1.31 and EX is 1. So this is based on the previous defined code, and we want to check the device in the design code. So this is the design code. This is the latest version of AISC 316. We're using the lateral resisting force method, and here is the D. You can see that D is seismic category D. This system is permitted in any kind of region. So I want to use C, and this is special moment frame. It's not special moment frame, and it's a special continuously brass frame. So we use this, and the other parameter is automatically getting, such as the limit deflection in the beam column. So this one, okay. And next, we define the combination in the program. Already added the available combination. So I'm going to call design. So we used automatic selection section. So the program will do more iteration to get the proper frame or profile for the structure. So it needs some time to iterate and verify the final profile. So wait for a while. Now the design is completed, but some of the beam column didn't pass. We should check here, which is called verify analysis with design section is called. Yes, and then we want to call verify all member passed. All steel frame is passed, and we want to check. So there is nothing left, and we can see. We can go to the, let's go to XZ, and just in this elevation we can see the IP section 300, 330 and 330, and the last one is 27, and it's finally passed, and we finished the design part, and we also can do some let's go to the extrude to see how it looks like. Yeah, it looks like this one, and this is the finished, and we can export this to even Revit. We can go to the Revit to do some detailing, and also other software using IFC to export to the import to the Tekla structure to do some detailing. Even to the AutoCAD, we can then create detailing. So the detailing is not too difficult, just using this BIM software to create sheets and also detailing. Now we stop here, and the next tutorial we will do the detailing using CSI CAD software, CSIX software, and also designing the connection. Okay, that's all. We will see you next time.
Hello everyone, this is a SAP2000 tutorial. In this tutorial we're going to conduct a pushover analysis of an RC frame structure using higher modes. Pushover analysis and nonlinear static analysis. There is three type of pushover analysis. So one of the pushover analysis considering the move shape of a structure, but in some research the authors intend to use higher modes of the, like second mode, third mode, even mode 5, like this. So then we will compare with a simple technique without a mode, or just considering the displacement in a specific U or Y direction. Now for this tutorial we consider have a 4-story RC frame structure which has a 3 bay. The first bay has a 3 meters length, and the second, or the middle part, is 6 meters, and with a little different to see how these affect. And the typical height is 3 meters from the first story to top story, and we assume have a beam section 30 by 40 centimeters and a column 30 by 30. The concrete is 400 psi, which is equal to 30 or 25 megapascal in a metric unit, and a rebar is grade 60, which has a 413 megapascal yield strength. And I should say the pushover analysis always conducted for assessment of an existing buildings. So it means we will do the analysis to see how the structure responds, how the structure performance can be evaluated based on the target displacement, or considering the smooth shape of a structure. So from all these things, we understand the structure should be designed, even exist in the field, in the site, and then we will evaluate the structure earthquake response. So we assume our structure has a live load of 10 km per meter, because we considering a 2D element and applying the load on each element, which is per meter. The second is super dead load, 15 kilonewton per meter. And lastly, when we have this live load and dead load, we must determine the lateral load of that structure based on the equivalent lateral force method. And after that, we apply that load in the node or edge stories. We assume it's 50 kilonewton per node from top to bottom. Then I will tell you it will become a triangular. This suppose the last floor is 50 and the second is cumulated with this one become 100, and then we can turn 150, and finally the base will be 200. So we jump to the program, and here is the program. We will take a simple new model, and you can fix the unit, use kilonewton meter centigrade, and whatever location you want. So it's depending on the material that you use. So I use United States material because we're already giving PSI and grade 16, which is from United States. So one more thing is you also can draw manually using grid, but for the simplicity and quick fast, and we need to use 2D element, 3D frame. It's a portal frame, and I give automatically 4 stories, and I come back to here, edit grid, and I want to give one more and activate this one, check this one. The first one is 4, and then it's 6, and then it's again 4. So we don't have anything in the y direction, in that direction, and the z is already here, so we're okay. And we come to the section properties. We're gonna call add a copy and change to the concrete, and we using triangular called column 30 by 30, and I change the size to 30 by 30, and the material is here already taken. And we come to the concrete reinforcement detailing, and we want to use the exact grade 60 and the design type, which means in case if you want design, you must select this one, and also for the analysis you must check this one. So column type, this is a column, and this is an existing building. So this is an existing building right now. This typical has 3 by 3, number 8. So but I'm not going to use that one. Make it a weak column, 2 by 2, and the diameter is 20 millimeter. And the confinement or strap size is number 4. You can come to here and check it number 10 or 8D, and this 3 by 3 is okay. Now you can see we have this existing column, so we're okay. And I take a copy, a new one, and I'm gonna call it beams, or beam 30 by 40, and this is 40, and this is 30. The same materials, we come to here, this is beam, and we assume this beam is checking the beam, and cover is okay. and okay. So now we define two elements, and okay. Now here we select beam for the beams and select column for the columns. Now the structure is automatically modeled in a 3D frame. So and for now I need just one window is okay. And the second is we assume the bottom is fixed. Come to the sign, join, restrain, and fixed. The second is I must define some load pattern to define the load pattern. The first one is dead load, and again I am come to the ST or super dead load. You can select other, and super dead load is coming. So between dead load and super dead load is that the self load, which is multiplied by 1. So the super dead load is will be 0. Again I can call it live load, and click live load. And the last one is called lat, and it's called L. Now you can select other or seismic, but seismic maybe you should choose a proper design code or analysis code. So I need other, just add. Now we have 4 load patterns. Okay, and I can select all the beams, and go to the assign and frame load, and I'm going to call distributed load. So dead load is self load, and when a super dead load is a 10 kilonewton per meter. Apply, and so the dead load is applied, and you can see here clearly previous selection, this command previous selection, and assign this time a live load. I think the dead load was 15, and that was 10. So this is again 10, and again I come to the previous selection, and I change that SD load to 15. Now there is one command here in case if I want to add 5 more in the same load pattern, then I call add to existing load, or I can replace 10 to 15. So now we are done here in the load. I come to here, just click this element, and you come to the this is the load. Right click and come to the load, and you can see here SD is 10 once, and again 5 again. So 10 in a global direction, 5, total 15, and live load is 10. Now this time we assign the lateral load in this node. So assign, this is joint load as a force. So this is a triangular shape. I come to the lateral load and giving it a global x50. So you know when we have 15 here, then this will be accumulated with the second floor, 10, 100, 115, 200. So exactly it will be like this. Now okay. Now we have finished. This is an existing building, applying all the loads, including the equivalent lateral load from the self load of the structure. Now what's next? We must define some sort of nonlinear behavior. So we have a distributed model which is not applicable here. We use we call it concentrically method, or hinge, or rotational hinge technique. We define hinges for the beam columns. For this purpose, we need to come to the section, come to hinge properties. We must define the hinges in concrete, and we call column. And there is 2 types of hinge. One is called force control, and the second is deformation control. You can as a parametric analysis, you can consider one's force control and the second deformation. Then you see how it looks like. And you should know the column always will be under the compression, moment, and shear. So therefore we need these things, which is called major moment, minor moment, and axial force. You can also define something here, such as the SF, and use that SF you can increase or reduce, and the moment curvature, in case if you already determine the moment curvature of that column, you can give that one, and some other parameters. So I keep this as default, and we also have other option here in case of in this circle condition, and you can also using double asymmetric bottom MYZ, you can see the changes. So I select this one, the first one. You can change in case and you see how it works. So okay and okay. So now the first hinge for the column is defined. The second, we want to come to the same method. This time we call beam. For the beam, the major effect will come from the moment 3, which is the maximum moment. So you also can determine the yield strength of that section or moment and you also can determine the immediate occupancy and life safety collapse prevention of the element. So I keep it as a default and say okay and okay. So now we define here is we should assign those hinges to the existing beam columns. So come to the here called frame, here is called hinges. So we assign beam in the, you can consider 0 or you can consider 10% of the length of that element from one direction, and you have to define in some element you can just give the hinges in one end or even in the middle of that beam. In some case you can apply 2 hinges. So but most popular is the 2 hinge in each element or edge beams. Now we can select columns. We select columns, and again we came to here column. I can delete this one, and it's called column. Again 0.1 and 0.9. So okay, and now the beam and column hinges are applied. And one more thing, because we want to apply or we conduct a modal analysis, and we should define the mass source or how the mass comes to this structure. So we go to the define here, it's called mass source. In the mass source we want to modify the existing mass, and we're going to remove this one, we're going to specify. So this one means 100% of the mass come from the self weight of the structure, and the dead load is also, super dead load is also permanent load, and the live load is 0.25% based on the code, and the lateral load is not considered. And okay and okay. Now we can define some sort of constraint to each level. So that means all these levels should work as a single element or single rigid floor. So for this we must define some diaphragms or multi-constraint points. So okay, I can come to here first. In the joint constraint, I can define a diaphragm or equal equation also, and that too is diaphragm and equal equation can be applied. So diaphragm is okay, add new constraint, it's called diaphragm 1, and the vertical direction should be fixed, and it's already rigid, in case if it's semi-rigid, then you can have semi-rigid. Okay, diaphragm 1. And we also can make it multiple to 2 and 3 and 4. So totally we have 4. So okay, and now I'm gonna assign those things called joint and constraint. In the constraint we have 4 applying this one, and we have created. If I go to the 3D shape, you can see. So it's not here, and if you go to here, then you can check the okay, you can check actually there, but this point showing that there is constraint this 4 node in a one direction. So I'm going to back again to the XZ and selecting these elements and getting 3 and the last one and 2 in here. So we are done with defining this one. Now we go to the load cases. This is which is the important part, and we must conduct a modal analysis. And when you modify, you can change the mode to rates factor and to the rates factor, and so SP8 is okay for the 4 stories, which is multiplied by the story. And here we must define the the masses come here, and the load applies. So don't need this one. We can actually consider the acceleration, actually not the load. We want to apply the load, which is deformation, and to give us the displacement, it should reach to the at least 95% of the mass participation. So it's X, and we also can ask for the Z, so vertical, because we have 2D. Just we ask X and we ask Y or Z. So this is 2. It means mode shape in the X direction, which is getting the natural period and frequency. This Z direction in vertical. And I should say, when you're defining UZ, that you have to bring some changes to the mass source. Okay, and okay. But before that, in the mass source, modify, and you should here is not, but the vertical mass should be considered. So it's okay. And the last thing, we must define the before we applying the pushover, we must define a nonlinear analysis of this load. So now add a new one, and I must call it non SD non-date load, and selecting nonlinear and defining this one, date load. This you can add a new one, and again we call it nonlinear super date load. And this time here the initial condition should be from the first self date load of the structure, and then we take SD load, and okay again, and this time is going to be non-life load, and initial stiffness count should be from this one, and here we should select life load and nonlinear. So okay. In the last part we have one more thing. We considering the lateral load, which the initial stiffness would come from the last nonlinear life load, and here is nonlinear lateral load. So okay, and now we are going to define we want to define the pushover. Pushover, we considering initial stiffness come to the this one, which is the last one here, and load pattern should be so in here we should check the nonlinear, then you can comes to here, and it's called mood. So mood 1, load type is mood 1 and a scale of 1, and we also can consider mood 2. So the first one is pushover mood 1, and for this reason we must use the load application. That means considering the mood direction 1 using the displacement control. And here is one thing I want to say, the called monitoring displacement magnitude or target displacement. How we can determine this one is not difficult. We use the yield point of that structure. So if it's a steel structure, so the yield point is 1% of the drift. So when it's concrete, it's in the actually immediate occupancy is 1, in another step is 1.5%, like this. But we want something larger displacement to observe how the structure responds during that large or 5% or 10% of the drift. So now let's suppose we want 10% of the structure height should the structure push, and then we want to evaluate how the structure responds. Now we have 4 story, each story has 3 with total 12 meters. So 10% of that 12 meter is 1.2, which is equal 10% of the drift. So joint 1 is exactly maybe this point or this point, and okay, 10% drift. And the second is the results should be saved in multiple steps, and this is the nonlinear parameters. You can use different solution scheme and also change this parameter. Keep it as default is good. And here is called one more thing here is called continue analysis if no convergence. You don't know if there is no convergence, so the structure will stop. You also can say yes, but it means taking too much time to complete at least that 100 steps. So that is okay, and no okay, and we're gonna say okay. And the same, I'm gonna copy the same thing, but except we're gonna using mode 2, modify, and mode 2 is okay. Now we already ran to the analysis, and we're gonna save the model, and I'm gonna save it here and run the analysis. So remember, this is a nonlinear analysis. It's a little time consuming than a normal linear analysis. So it's run the analysis, and we're gonna run. Yeah, let's start running. The analysis completed, and there is no error. Some warning, we keep it, we ignore them, and we directly go to the for the pushover mode 1. But before that, let's go to the modal analysis, and we go to see mode 1. Mode 1 is this direction, and it has a time period of 0.7, which is acceptable. And we come to the first pushover analysis, and you can see here some hinges appeared, below 1, and I can come to here 2 and 3, step 3. And I should say one thing which is different with ETABS. If you consider the mood shape, you will not see in ETABS these things, but in SAP it's possible to see the hinge location. Mood 4, 5 still is in the life safety, and now collapse prevention. So step 9 and step. So there is 9 step, and we have collapse prevention, and we go to the okay, this we cannot compare here, and we can display, and we want to go show static pushover curve. So this is the curve, which is very nice. The structure has a capacity of 400 kilonewton and with a displacement of almost 1.2 meter. And we also go to the mood. This is mood 1 and mood 2. Pushover. One was pushover and one was mood 2. I must check it in the. Yeah, this is mood 2. Yes, this is mood 2. So the name is a little different. So mood 1, mood 2, and I must go to here because the direction of mode 1 was this direction, so this become positive and that become negative. Now here is the issue that you see the mode 2 is result is not acceptable. So in this mode 1 is acceptable and it's quite okay. So in this reason we in some case we compare mode 2 with mode 1 to evaluate the structure. So the mode 1 is which is the fundamental mode of the structure, so we usually use mode 1, and from that fundamental we take the structure time period and also natural frequency. Now if I unlock and check it with a direct displacement, so the result will be 95% same with that. So if I go back quickly here and define a load case, and I want to add one more. Let's call it pushover this. So instead of applying mode, we're gonna use displacement. So the displacement or acceleration in the U1, and with a factor of 1. And we come to the load control. Here we give again that 1.2 meter push in the U1 direction, and here multiple state, and other thing is be default. So I should say one more thing. Select this node, and I want to see what node is this exactly. This is node 5, which means applying the load is in this direction. So now I can come to the analysis, and I want to see the load case to run, and I'm going to run. So the analysis again completed, but this time we got error because so there is error. I know where is the error because we have some mistake here. I must come to the define load case and push over displacement, and must modify this one, and I should use this one in the last case, and that's it. Okay, and I go to run the analysis again. Now you can see the error is fixed and the warning 3 is okay. Now we go back to the display, and we go to the, here is the mode 1, and it should be close to this pushover displacement. So it's 400 megapascal kilonewton resisting force with this displacement. So we come here, and it's above 450, which I said exactly the same. Now this is the end of the tutorial. If you have any question, please put in the comment. In fact, I'll see you next time.
Bismillahirrahmanirrahim. Hello everyone. In this video tutorial, I'm going to show you how to model a 10-story steel structure in SAP software and perform a time history analysis. So here is when we get new model, and we can see some template here. So I can use, for convenience, I can use 3D frames, just 3D frames, and I'm going to give the number of stories 10 and the number of bays in X direction 5, and the Y direction is also 5. The story height is typically 3 meters. The weight is about 6 meters. So I can quickly draw a column that should be box column using this box column, and the size should be 50 by 50, and this should be something, the flange 0. Actually it's quite the same. We can take it 0.20, which is almost 20 millimeters, and the wave is also 0.02. Still is FY 15. So you can columns. Okay, and next is the beam. Beam is going to use I section that's called beams. This is T30, which is the height of the structure, height of the beam, which is be about 60 centimeters, or 0.5 meters, and the weight is about 50 centimeters. So the flange is 0.020, and the wave is 0.015, and this flange, bottom flange, is same with top flange. And sorry, this is this bottom flange width, which is about 50, and the thickness is here 0.020. So the wave is 50 millimeters. So we are done, and okay, we can go to select beams and select columns. Okay, now for to performing a time history analysis, we just select the base and apply a boundary condition. Let's see, the boundary condition is fixed in the base. It's done, and we don't want to apply any other kind of loads, and we quickly go to the load cases. For time history analysis, it's require modal analysis. The modal analysis should perform a Ritz vector or eigenvector. So I prefer to use eigenvector. The number of modes should be 20, and at least should be 1. I can select load patterns, date, here acceleration, and one more in the Y direction. So other parameter is default. So the mass sources will take the date load, the entire date load. And now we can go to define a function, time history function. We can use cosines or sine function. Also, we can bring the from file which is already saved. Add new function. We should go to the browser, and if we have any recorded time histories, here is time history, some pre-defined in the directory, set a SAP2000 directory. We can select here, but if we don't have any specific specific, we can select, go to the pure ground motion database and download. So I have another video, you can check how we can download this data and how we can use it to the SAP or ATAP software. So I'm going to use this new all. This is the time history is using, we can view. So this is line 1, line 2, line 3 should start, and the time period is 0.20 second, and it's about 3000 point. Is 3000 point, and the unit is centimeters per square second. So I'm going to fix this one. One more, I am gonna see how many lines has per one. We can just in case here 1 2 3 4 5 6 7 8. So this is called 8 numbers per line. This is one line, and each line has 8 number. So I can give 2, it should escape, it go to the 3, and this should be 8, and the time period should be 0.02 second. Now we can display, this is the time history. So the total is about 1 minute. I can call new all x, or you can write north or east west. And another is also the same, but this time I'm going to bring the y, or new all number 2, the same for, and here is 0.02. I'm going to see it's also 1 minute. I should make a modify, that's this, write the name. It's called new home y. Okay, so this is completed. We go to the back again to the define menus. Here go to load cases, and we can add a new load case. So this time I can select time history. So it's time history. From load case tab we can select time history, and from another tab we can consider linear and nonlinear. So for simplicity, it take least time, linear, and the solution should be modal based. And here we can select acceleration in U1, so modify, and this time we select here y, and so here is modal scale factor, which we have centimeters, but we're using meters, so it should be 0.01. Modify, and it should be 0.01. So how we can get this is here, we have centimeter, 1 centimeter giving this number meter per square second. So, and we have about 60 second calculator. I can have 60 divided by 0.02. So this is the time it requires 3000 points. and the step is 0.2. The modal damping, we assume 5% inherent damping, and okay. Now we are going to save our model, or we can go to, sorry, I'm going to use tennis to be steel structure. Time history. I can select this time history, yes. So now we can perform the analysis. The analysis completed because it was linear. It quickly solved. So we have one error that's called yeah. So that's the model case error, and that doesn't require anything. Now we can see from that self load some deflection quite less, and I can go to check millimeters during that the self wait, we can see this node. Let's see if we can get this. So this point is about in the z direction about less than 1 millimeters. We can go to the deformation and select this one, and we can select some let's see about 10 seconds, and we can draw the graph. And yeah, here is a deformation during the time period of 10 seconds. And if I go to start animation, and it's going to animate so this is the animation of that. Also we can create some videos and also we can display here we called plot function. So from plot function we can get time histories, this point. If you want, you can select this point or any point. So this is object 66. I'm going to display and here is plot function. I can go to define a plot, and here is called joint displacement, and here is add plot function. So we should give the ID number of that joint, and here is acceleration and in which direction, x, z. We both have, we are going to select x first, and this is x, and go to another one, so the same but this time going to y direction. So this is it. Okay, and first we're gonna add the horizontal function plot should be time, and we can display. This is it. So we got this location, these joints, accelerations. So we can go to back, remove this, and put this one in a y direction. This is the y direction. So display. This is y direction. And also we can go to define, and this time going to joint output, joint displacement, add plot, and this time we're going to use the same area, the same nodes, but we are going to use displacement. from we can select absolute displacement or absolute acceleration into x direction and go to the same. This is y direction. Sorry, you should give 60. Okay, now we can go to this one is bring this, and this two is the first one is this one is x direction displacement, and this is y. Okay, now we can see the displacement when the structure encounter this such kind of earth ground motion. We will see this. And the last one is this is 3, and this is in y direction, this direction. So here the maximum displacement is 75 millimeters. So we are done. If we want to create a video, but we have to save let's see, save this plot function. We can have it displacement or acceleration. Remove. I'm going to save it. Let's see, call it new save. We call it acceleration, ACC. So we save, and now we can go to here, create a video file. So create a video, can multi-step animation. We can we can select here, select the same name, and show graph, and starting 0, and the time can be 0.20, which is, so we can magnify this factor 10. And okay, it takes some time to create a video. Yeah, here is good. We can see it's better to see. And this is a video. And this is the beginning, and we can reach to this large or peak ground motion. Again, we can see large displacement. It takes 1 minute. Now it's going to follow. We can obviously see the deformation. Yes. Yeah. The structure is shaking like an earthquake. So we applied both direction. If we use 3 direction, that will be total realistic. Okay, we are done, and this is actually creating. After end, then the video will be created. So this is the end of our tutorial. If there is any question regarding to time history analysis, and put your comment in the below description in the comment area. I will find time to answer your question. See you for next time. Hello everyone, this is another tutorial. In this tutorial, I'm going to show you how to model the cooling tower in SAP2000. So after we finish this modeling, we will conduct some analysis, such as time history analysis, to see the response of this structure. And also, we will use Abacus to evaluate the behavior and also the frequencies and time period. So this is about 117 meters diameter in the bottom and 68 in the top. So we want to model this. So how we can model this? So the bottom part is mostly use beam columns, and the top wall is shell elements. So we should create this one, and I'm going to SAP and selecting meter grid only, and these 2 grid in the X, 1 in the Y, and 3 in the Z. So the X direction is equal this one divided by 2, 58.5, 58.5, and this is just as it is, keep it first. And now we can delete one of the windows, and I can go to the one of the elevation. And now I want to give the height of the tower. So the height of tower is equal the first column 13 meters, and the total height of the cooling tower 162 meters. 162 meters. So I can say OK. So this is it, and now I want to create some nodes or some joints. One is here, which that node is equal the diameter, the top diameter divided by 2 in this point, and the second is a joint in this point. So the z is minus 37, and this one minus 65.3, and then in the x direction we reduce that. So we can choose this point and then create one node here. So that first node is equal, and the top divided by 2, which is 68 meters. So divided by 2 becomes 34. So I'm going to pushing one point here, and we got one joint. And the second joint is here. We're putting pressing here, and then we got minus 1.35, and then z is equal to this height, 37 meters. And I'm going to give 37 minus 37, and I can put this point here. Now we created 2 points, and selecting, please turn on the label. OK. Now we're going to select the drawing a curve frame or element, selecting here and a curve frame. So I'm gonna selecting this point and the last point. So it will open another window, and it asks me to choose. So the line object is curve, and I want to select parabolic arc third point ID. So it will automatically select the third point on the ID is 2. So I want to create that curve in different point here, and now we created a curve. So the next, I want to delete this. I want to delete this node, so there's no need anymore, and select, take again one straight line or straight frame, and from this point to this point we need to just create the shell path first. Now I'm going to select these 3 joints, and I'm going to edit and line called divide or break. So I'm using break at intersection, and that's OK. And we want to delete this bottom part of the element. So just we have this. Now we can select all, and then go to edit, and using extrude line to area. So using radial and selecting the Z, and the angle is T, the number is 36, which is the complete one circle. So I'm going to 3D, and this is the shell part. So now we're going to go to the bottom for the column. We're going to go to the here, rotate this, you can use this rotate now we want to draw the bottom columns. Now we want to draw a joint. The special joint, draw here. Create one joint, and I wanna duplicate this joint. Going to edit and call replicate in Modal using parallel to Z, and the number is 10, the angle is also 10. So I'm going to keep, do not delete. Okay. So now we create it. So now we want to draw a beam in this, between these two joints. And next I want to select this again, and from this to here to middle of this point I want to draw one column. Okay, and rotate the ladle and just taking again this line and these two here. Now we can delete the bottom, this area, these parts, delete, and this is no need. And I want to restrain this joint sign and go to joint, restraint, and using fixed. Now I want to select the entire these columns, and I'm going to duplicate using replicate here, and totally using a radio parallel, and the number is 35, and going to we have 1 and 25, and totally we created the entire columns. So now the modeling is completed. So one more thing, that the shell axis should be reversed on this side. Go to here, shell area, and call reverse axis. So I'm going to apply it. Now the color is changed. So now the model is completed. The model is completed, and you can go to view here, because the restraint is not shown. You can go to here and click restraint. Okay. Now the modeling is completed, so we will conduct some analysis and also defining some section, especially column and shell parts. So this is the modeling of cooling tower. This is very one of the most infrastructure in developing countries. So that's all. If you have any question, please put in the comment, and see you for the next tutorial. Hello everyone, this is another tutorial. In this tutorial, I'm going to show you how to conduct a modal analysis on cooling tower using SAP software. In the previous, I have created the modeling part. In this part, we will conduct a defining section and also considering a model analysis. Just select one of the shell elements, and you can right click and see what is that shell. So this is a shell elements ASC. So just I'm going to define, go to the define, and the section here is called area section, and I want to change that shell, modify to using membrane and bending elements to 1 meter or 80 centimeters. The material is using concrete, so I'm going to select add new material using concrete, and I'm going to use the lightweight concrete 60. Now you can select here, so it's okay. And next I want to change the beam cross section. So I'm going to select it here. It's F section. So I'm going to go to define section, and I'm going to frame section, and I'm going to add new section. So this time I used concrete using circular. So the circular is called the diameter is let me show you one example. Here is a research which is almost the same, and I'm going to use the techniques, the size of the column which is used in this study. Now let's go to here. Here is the thickness of column height and the number of column and the column diameter. So the column diameter is 0.7, so it becomes 1.4 meters diameter. Now I can use this one. The diameter is 0.7. So mine is a little larger, so I will take the same thickness with as a shell, so it's 0.8. The material we're using is the previous lightweight material. Now, okay, and here in the select, I go to select. Here I call properties frame section. So I want to select the previous one here. Now I want to add it my own properties. So I'm going to column or C. So now it is it. Now you can see the we can use this option, this one, and close to here, and we can see the column. If I go to use extrusion, and you can comes to here and use extrusion, say okay, and you can see the column. Now the next we go to the define. In the define we want to consider the mass sources. So we will not adding any extra live load, and just we will take the self load of the structure. So we can go to a modify, and it's called elements self mass and additional load. So that's the self load. We not consider. If you consider, just go to dead load is 100% of the structure load. Now we go to the define here in the load cases. In the load cases, we already have dead load and we have modal. In the modal, we have two kind of mode analysis. So one is eigenvector and one is rates. So I prefer to use rate factor, and this is the height of the structure is about 162 meters, so very quite high, and the number of modes is depending to the height of the height of or number of stories. So the number of stories almost there is 2, because the shape of hyperbolic is changing in 2 points. One is the bottom and one is in the top. If I go back to here, so that 10 mode shape is okay. So that 10 mode shape can participate in all can get the all directions. So I'm going to add it acceleration in the X and acceleration in the Y. Add 2 I's, and this time changing the Y. Just modifying is, so I consider 99%. So in this 10 mode it can reach to 99, but for that to 90 is enough, which is the code required to be over 85, and the last one is also 90. Sometimes we can't reach that 99, so it's 19 is okay. Now we don't have anything else, so the so we're not considering the nonlinear analysis, just a model, and I'm okay and okay. Now we can go to run the model and run it. So we didn't create any mesh because the shell distribution is quite less, so 10 meters 10 meters, so that's okay. In case if I create more fine mesh, so it take more times. So now the analysis completed. It's the deformed shape, and I'm into 3D, and I go to the see some deformation here, and it is this meters, and I'm going to show millimeter. Millimeter, and you can see here. So this is about less than 1 millimeter. In the Z is 21 millimeter. So the deformation is not quite too large, but we're gonna see the mode shape. And here is the date load, and I'm going to consider a modal and using mode, and also drawing some contour in the X and the Y. We don't have any Hinge property to see the life safety or immediate occupancy, and we can go to here, okay. And this is the first mode shape. The first mode shape time period is 0.7 second, so approximately it's okay. And we can go to the display option, and let's show the table, and here is called structure output, and it's called modal information. I'm going to modal load participation, and we need to see mass participation, and also that's okay. Now we can see in that 20 node it didn't reach to 90%. So what we should do, well, we need to increase the number of mode shape to reach that at least 60%, 85%. So what we're gonna do is I'm gonna unlock the model and go to define again. And here in the load case, and I'm going to show model, and this time I'm going to use 20 mode shape. Now it's okay, and rerun the model. It's completed, and it is the time period is 1.12 second. So this is 160. So this is almost acceptable in case if you want to use that equation 0.1 times n, which is the number of story. So this is okay because it's almost one story here and one story here and one story here, total story. And we can go to again to the display option and show table, and I'm going to okay, and we want to see the mass participation. Mass participation, yes, and the mass participation is UX. Yeah, it's reached in the mode which mode this mode is completed. In the mode let's see, we had 10 mode shape, but in the 10 mode didn't finish. In this mode is completed, so now it's 100%. 100% from this here to 8 to from the 6 is completed. So this is 100% of mass participation. In the previous 10 it didn't complete it, so we can say it is now model analysis completed. So the first mode shape is I'm going to show animation. So this is the first mode animation, and I can go to second mode. This is the second mode shape. So one was in this direction, which is X, another is Y. Now I'm going to comes to display, and in here is also okay. We can go here, and here show the contour, and also I want to, okay, now it's showing, we can see get the maximum displacement. So the maximum displacement is -8. So -8, we can go to select one node and see it. So this is in U1, in U1, so in the X direction, so this one. And in the first mode, we can select this, also negative U1, and we can go to the other modes, mode 2, mode 3. So this is mode 3, and we can see the maximum is +7.8 millimeters. Okay, now we can also see some stress or shear force across the beam columns, and also axial force from date load. So let's go to suppose see the FE1. It's very less. We can go to using this shell stress, and I'm going to in first direction, I'm going to second direction, or we can use the S max. So now we can see the stress is quite less in the bottom here, and here is less than. But we use the kilonewton, so it's a little different. I should use which we can get megapascal, and now you can see 0.3 megapascal. So the concrete is 60 megapascal, so very less. So why this structure is quite sustainable for with this very tall? Because the system, hyperbolic system, is quite strong structure. So this is finished the model analysis, and next we will conduct a dynamic analysis. See you next time.